Bismillahirrahmanirrahim. Welcome in the class. So, our today's topic of the discussion is Hermite-Hadamard inequalities for K fractional uh, operators. So, in fact, I just want to tell you that different authors have proved the fractional integral inequalities of Hermite-Hadamard types for different fractional integrals. So today we shall discuss how they are interesting and how these are generalized. I have told you already in the class about the Riemann-Liouville fractional integral. So this is the general case because for k is equal to 1 means special value of the k we can get the definition as I already told you in the previous class. So mainly we shall use the convexity of the function to establish the Hermite-Hadamard type inequalities. So without any delay, we shall start from the main results. So in just here, you can see in the reference number 3, the definition of the k gamma function given by the Diaz. So definition 3, in fact, you people know very well about aware of the definition of the k gamma function. In fact, the gamma function for particular k is equal to 1 here if we use, then you will get the standard gamma functions. So because why we need this, in fact, we want to generalize the definition of the Riemann-Liouville fractional integral, and we need the definition of the k gamma functions, which is given in the definition 3. So definition 4, which is given in the reference 7, for these we have a parameter k which is positive, and f is integrable function over the interval a, b, and for non-negative value of a, the k Riemann-Liouville function which is defined by this and this. These are the notations. For real valued function f mu are given here. These are these two definitions. So these are respectively called the upper one, this one. This one is called the left-sided Riemann-Liouville k fractional integral, and the lower one is the right-sided k Riemann-Liouville fractional integrals. So this is the thing which I already told you in a couple of minutes before. For the particular value of the k, I mean k is equal to 1, you can get the classical definition of the Riemann-Liouville fractional integrals, which already we have discussed in the class. So here is the first main results which is proved by me and my different co-author in theorem number 5. So this is the Hermite-Hadamard type inequalities for the k Riemann-Liouville fractional integral, which is in fact a generalized case of the some results for k is equal to 1 we can get. So for k greater than 0, and these are the two left-sided and respectively the right-sided Riemann-Liouville fractional integral, and here is the lambda, the parameter lambda greater than 0, which is the order of the Riemann-Liouville fractional integrals, and we have the f from a, b to r with a positive mapping with the condition that f is integrable. F belongs to L1 AB, and if f is convex on the interval AB, then we have the inequality given in 8, this inequality. So in fact our purpose is to prove this 8 inequality given in 8. So you can see this is the Hermite-Hadamard type inequality, because Hermite-Hadamard type inequality, what states that f of a plus b by 2 less than equal to, here is the central term which is in fact the average of the integrals, but we have replaced it with the average value of the Riemann-Liouville fractional integral and less than equal to the average value of the values of the function over the interval AB. So we want to prove this one. For this, let's begin with the proof. So our proof starts from here. If f is convex, so simply if we use the definition of the convex, orally I can tell you f of lambda x plus 1 minus lambda y less than equal to lambda f of x plus 1 minus lambda f of y. For particular value of the lambda is equal to 1 by 2, here is the half which is must belong to the interval AB, we can have the inequality this one, 9, which is given in 9. So now we want to make some special substitution to achieve the main task. So in 9, if we replace this xi is equal to mu of a is equal plus 1 minus mu of b, and eta is given in this expression, this inequality. If we put this value of xi and eta in 9, we can get the inequality number 10, which is given here. So just to make it more interesting and to get the favorable result, I will multiply the inequality number 10 with this special term. This is a special chosen term, because this term will give us the result we want to prove it, and then integrate the over interval over 0 1. Why we can interpret it, how we can do this? In fact, the chosen f must belongs to the L1AB, so therefore we are allowed to integrate it. So after integrating, what we can have, so multiplying this one, we can get this inequality number 11. So simple. If we can call these two integral and denote it I1, this is the integral I1, this is the I1 highlighted, and this is the I2. So now we want to solve it, the I1 and I2. So by taking this substitution, by taking this one is equal to phi in I1 and mu of b is equal to omega in I2. If we replace these two in the inequality number 11, then what we can get, the above I1 and I2 will take this form, these two forms. And just at the end, what we need to do it, substitute the value of this I1 and this I2 from 12 and 13 in 11, then 11 becomes this one, this one, which implies that f of a plus b by 2 is give this one, and this term will be taken in this side after multiplication and division, elementary mathematics, and this one becomes this one after substitution. If you carefully observe and see the definition of K Riemann-Liouville fractional integral, which is given above, I told you this inequality becomes this one. So this becomes this one as we have used the notation above. We get the inequality number 14. So this 14. So this proves the one inequality, because there is given in the double inequality 2 times less than equal to. This includes the first inequality given in 8. To complete the second one, we have to repeat the same exercise, similar exercise, but carefully with the different substitution, different parameters, different settings. So this will be if f is convex on tau belongs to this is the standard definition of the convexity, convex function. Jensen's inequality I told you already. So if we use this one, so and f of mu b is this one. So above add the two inequalities. Above given add the two inequalities, left sided added in the left side, and the right sided becomes this one after some addition and cancellation of the term. Obviously will give us the inequality number 15. So multiply the inequality number 15 by this chosen special term on the both sides, and then integrating over the interval 0 1. 0 1, what we can get? Surely we can get the inequality number 16, and above the two integral I1 I2, and in this case these are the two integral which becomes this one and this one. Let us call it K1 and K2. Now we have to in fact simplify K1 K2 and want to rewrite in standard form as earlier we did. So in 16, if we make some special substitutions, we get this one after some integrating, and this one, which implies this one. So this becomes the right side, left sided, and this becomes the right sided Riemann-Liouville fraction integral used here. So by combining 17 and 18, we get 17 and 19, we get the 8. So this is the main result we have proved. So as a remark, I can make you one thing very clear, that for particular value of k is equal to 1, we can get the Hermite-Hadamard inequalities for Riemann-Liouville fractional integral, which is earlier proved by some different authors. So this you can see in the references. So I strongly recommend you to read and read the things very carefully, and you can see what is the interesting here. Obviously, this is the idea which I want to give you. So you can improve it, you can generalize it by using the different functions, different spaces, different fractional integral, even more generalized fractional integrals. I'm sure that many mathematicians, many researchers have generalized it, but research point of view, you can think, if you think critically, then you will be able to observe and find and learn something new. So I strongly recommend you to read it very carefully. So this is our first main result. Let's talk about the second result. This is the lemma 2.1. So in lemma, we have proved the equality which is given 20. So for the let's first state the inequality. We have k greater than 0, and these are the two left and right sided Riemann level function defined in definition 4. So definition 4, this is given previously. Obviously, I will share the same document to you through WhatsApp or through email. You can read it carefully. So we have the f be the differentiable mapping. We have taken this f as a differentiable mapping over the interval, this with the condition. And f prime is integrable over the interval ab. F prime belongs to LAB, means integral of f prime exists, and we have this equation given in 20. So let's begin with the proof. So for the proof, let us consider the I1, this one I, and which may be rewrite as just what I did, split the two term integral into two parts. Here this multiply by the f prime and separately simple. Let us call it that the first integral given in the square bracket is I1 and the second one is I2. First integrate the I1 by parts. First function integral of second, and second integral of, you know the formula. So integrating by parts, we can get the I1 like this one, and substitute this expression, this highlighted, as xi, and then after some calculation the integral I1 becomes this, which is given in 22. So you have to repeat the same exercise again for the I2, make some substitution. I have taken this one I2 and makes this substitution, this one as zeta, the I2 will becomes this one, and add the 22 and 23, you can exactly get this one. It follows that this one. And at the left side, what we are having, this I is this one, and right side is this one. So multiply the 24, this highlighted is 24. This whole is I24, 24. Multiply both sides by b minus a, and then you can get the required result, which I want to prove it. So this is the, again, this equality will allow you the more interesting results. This is the base for this. So this one we have proved. What we proved, let me show you the again starting point. This is the lemma 2.1. So now we have proved the two results previously and the lemma 2.1. So if you read and obviously if you understand that these two theorems, you will be able to understand the understand the Hermite, Hadamard type inequalities, and obviously the application of Riemann-Leibel fractional integral. So a fractional integral will you will be able to apply for this. So for the next result, I advise you to read by yourself the theorem number 6. But what makes it different from the previous two theorem? Here we have used the convexity of F prime, the convexity of F prime. And this is the lemma 2.1 we just proved before few minutes, few seconds. And the definition of F prime, convexity of the F prime, here it is. So by using the absolute value property of the integral less than equal to the value of this function, and integral is this, and mod is separately taken over this for every term, and we have made some setting here. F prime, this is the convexity of the F prime. Here is the F prime, and we use the convexity and get this one. Okay, so integral separated, and we have given the two integral k1 and k2. Likewise, solve the k1 and k2, multiply with the term you have previously done, and calculate k1 and k2. You will get these 27 and 28, and substitute the value of k1 and k2 in 26. You will get exact the 25. I'm little faster in this theorem. I was a little faster in this theorem, so you can read it by yourself. So next is application. We shall discuss in the physical class, in the classroom, hopefully. I recommend you to read the theorem results. If you didn't understand, you can contact me through my WhatsApp, phone calls, through emails, or in my office physically. Thank you very much for your kind attention.